This is Anag Agile Systems, an AI provider. Welcome to Machine Learning series. Today's video is titled Models Taxonomy. This video is about different models used in machine learning and deep learning techniques. This video is the result of a popular request from subscribers asking for more explanation about fundamental technical jargon used in our machine learning series. As this video is about modeling in machine learning, so we'll now explore different models of machine learning in detail. I'll try to explain them in as few words as possible and make it simple for you. So let's begin with the parametric models and non-parametric models. Parametric models can be defined as models that first make an assumption about a function form or shape of function f, that is linear function, then fits the model. This reduces estimating mapping function f to just estimating set of parameters, but if our assumptions was wrong, will lead to bad results. That means assumptions can greatly simplify the learning process, but can also limit what can be learned. Algorithms that simplify the function to a known form are called parametric machine learning algorithms. A learning model that summarizes data with a set of parameters of fixed size that is independent of the number of training examples is called a parametric model. No matter how much data you throw at a parametric model, it won't change its mind about how many parameters it needs. Some more examples of parametric machine learning algorithms include 1. Logistic regression, 2. Linear discriminant analysis, 3. Perceptron, 4. Navy-based algorithms, 5. Simple neural networks. Benefits of parametric machine learning algorithms are as follows. 1. They are simpler, that is, these methods are easier to understand and interpret results. 2. They are speed, that is, parametric models are very fast to learn from data. 3. They require less data, that is, they do not require as much training data and can work well even with the fit to the data is not perfect. Limitations of parametric machine learning algorithms. 1. Constrained, that is, by choosing a functional form, these methods are highly constrained to the specified form. 2. Limited complexity, that is, these methods are more suited to simpler problems. 3. Poor fit, that is, in practice these methods are unlikely to match the underlying mapping functions. Now let me explain you about the opposite of parametric functions, that is, non-parametric functions. Algorithms that do not make strong assumptions about the form of the mapping function are called non-parametric machine learning algorithms. By not making assumptions, they are free to learn any functional form from the training data. As non-parametric models that do not make any assumptions about function f, which allows them to fit a wider range of shapes, but may lead to overfitting. Non-parametric methods are good when you have a lot of data and no prior knowledge, and when you don't want to worry too much about choosing just the right features. Some more examples of popular non-parametric machine learning algorithms are 1. K-nearest neighbors, 2. Decision trees like CAT and C4.5, 3. Support vector machines. The benefits of non-parametric machine learning algorithms are as follows. 1. Flexibility, that is, capable of fitting a large number of functional forms. 2. Power, that is, no assumptions or weak assumptions about underlying functions. 3. Performance, that is, can result in higher performance models for predictions. The limitations of non-parametric machine learning algorithms are as follows. 1. More data, that is, it requires a lot more training data to estimate the mapping functions. 2. Non-parametric machine learnings are a bit slower, that is, a lot slower to train as they often have more parameters to train. 3rd, overfitting, that is, more of a risk to overfit the training data, and it is harder to explain why specific predictions are made. Now let me talk briefly about supervised versus unsupervised machine learning algorithms. Supervised models can be defined as models that fit input variables xi is equal to a tuple of x1, x2, up to xn to a known output variables yi is equal to a tuple of y1, y2, up to yn. That is, a supervised learning is where you have input variables x and an output variable y, and when you use an algorithm to learn the mapping function from the input to the output, y is equal to f of x. The goal is to approximate the mapping function so well that when you have a new input data x and that you can predict the output variables y for that data. It is called supervised learning because the process of an algorithm learning from the training dataset can be thought of as a teacher supervising the learning process. We know the correct answers. The algorithm iteratively makes predictions on the training data and is corrected by the teacher. Learning stops when the algorithm achieves an acceptable level of performance. Some popular examples of supervised machine learning algorithms are 1. Linear regression for regression problems, 2. Random forest for classification and regression problems, 3. Support vector machines for classification problems. The unsupervised models can be defined as models that take in input variables xi is equal to x1, x2 up to xn, but they do not have associated output to supervise the training. The goal is to understand the relationship between the variables or observations. That is, unsupervised learning is where you only have input data x and no corresponding output variables. The goal for unsupervised learning is to model the underlying structure or distribution in the data in order to learn more about the data. These are called unsupervised learning because, unlike supervised learning mentioned earlier, there is no correct answer and there is no teacher. Algorithms are left to their own devices to discover and present the interesting structure in the data. Some popular examples of unsupervised learning algorithms are 1. K-means for clustering algorithms, 2. A priori algorithm for association rule learning problems. Now let me describe briefly about Blackbox modeling versus descriptive machine learning modeling. Blackbox machine learning models are models that make decisions, but we do not know what happens under the hood. Example, deep learning neural networks. Descriptive machine learning models are models that provide insight into why they make their decisions. Examples, linear regression, decision trees. That is, black boxes are devices that do their job but in some unknown manner. Stuff goes in and stuff comes out, but how the sausage is made is completely impenetrable to outsiders. By contrast, we prefer models that are descriptive, meaning they provide some insight into why they are making their decisions. Theory-driven models are generally descriptive because they are explicit implementation of a particular well-developed theory. If you believe the theory, you have a reason to trust the underlying model and any resulting predictions. Certain machine learning models prove less opaque than the others. Linear regression models are descriptive because one can see exactly which variables receive the most weight and measure how much they contribute to the resulting prediction. Decision tree models enable you to follow the exact decision path used to make classifications. For example, our model denied you a home mortgage because your income is less than $10,000 per annum. You have a greater than $50,000 in credit card debt, and you have been unemployed over the past year. But the unfortunate truth is that black box modeling techniques such as deep learning can be extremely effective. Neural network models are generally completely opaque as to why they do what they do. Now let me talk briefly about first principle models and data-driven models. First principle models can be defined as models based on a prior belief of how the system under investigation works. incorporates domain knowledge on ad hoc basis. Data-driven models can be defined as models based on observed correlations between the input and output variables. First principle models are understanding of the system underlying physics to derive its mathematical representation. First principle models are expensive in development since expertise in the area of knowledge at the advanced level is required to derive equations from physical laws, while data-driven models use system test data to derive its mathematical representation. The advantage of the former approach is the depth of the insight into the behavior of the system, thus ability to predict the performance, while the advantage of the latter is the speed in which the accurate model can be constructed and confidence gained thanks to the use of the data obtained from the actual system. The difficulty of the former approach lies in the determination of the phenomenological parameters like the damping or the heat transfer coefficient. The first principle models are frequently adjusted by trial and error, which can lead to non-optimal results. On the other hand, the disadvantage of data-driven models is the need to handle multiple data sets in order to cover the range of system operations. Differences between first principles and data-driven model are as follows. First principle modeling requires less data with heavy dependency on domain knowledge, also high reliance on deep domain expertise. First principle model can handle highly non-linear and complex relations. First principle modeling requires complex computation which requires a lot of time to predict new relationships. Output of the first principles is highly interpretable, consistent, physically meaningful link between parameters. Data-driven modeling requires huge amount of data, namely big data, and it can provide useful results with less domain knowledge. Data-driven modeling cannot utilize high non-linear and complex relationships as it is limited by the range of values spanned by the training dataset. But data-driven modeling can quickly adapt to circumstances of a specific problem instance. Output interpretability is limited by the rigidity of the model function form. Now let us understand the intricacies of the deterministic and stochastic modeling. Deterministic models are defined as models that produce a single prediction, example yes or no, true or false. Stochastic models are defined as models that produce probability distribution over possible events. A deterministic model is a model where the material properties are well known, that is deterministic, none of them is random. And the applied load are also deterministic. A stochastic model has, on the other hand, has random properties. Example, the nth mode is a random variable with uniform distribution or normal distribution. And the applied load is also a random variable, for example, wind load, earthquake, etc. A deterministic model corresponds to a design, that is analytical design, in certain state. The stochastic model in a random analysis corresponds to a design in a risk state which uses probabilistic definitions. A deterministic model is one that uses numbers as input and produces numbers as output. A stochastic model includes a random component that uses distribution as one of the inputs and results in a distribution for the output. These distributions may reflect the uncertainty in what the input should be. For example, a deterministic input plus noise, or maybe reflect a random process, that is a stochastic input. Now let us understand the intricacies of the flat cluster models versus hierarchical cluster models. Flat models are models that solve problems on a single level or no notion of subproblems. Flat models are models that solve problems on a single level, no notion of subproblems. Hierarchical models are models that solve several different nested subproblems. Flat clustering can be defined as flat clustering is where the scientist tells the machine
how many categories to cluster the data into. Hierarchical clustering can be defined as hierarchical clustering is where the machine is allowed to decide how many clusters to create based on its algorithms. Flat clustering creates a flat set of clusters without any explicit structure that would relate clusters to each other. Hierarchical clustering creates a hierarchy of clusters. Two flat clustering algorithms are k-means, a hard clustering algorithm, and the expectation maximization or EM algorithm, a soft clustering algorithm. Fast clustering versus hierarchical clustering is as follows. Flat clustering algorithms are usually start with a random partial partitioning of documents into groups. Flat clustering algorithms refine iteratively. Flat clustering algorithms, main algorithms or popular algorithms is k-means. In hierarchical algorithms, they create a hierarchy. Hierarchical algorithms are usually bottom-up, also known as agglomerative. Hierarchical algorithms are top-down. They are known as divisive hierarchical algorithms. Hierarchical clustering, also known as hierarchical cluster analysis, is an algorithm that groups similar objects into groups called clusters. The endpoint is a set of clusters where each cluster is distinct from each other cluster, and objects within each cluster are broadly similar to each other. There are two types of hierarchical clustering, divisive and agglomerative methods. Divisive method can be explained as follows. In divisive or top-down clustering method, we assign all of the observations to a single cluster and then partition the cluster to two least similar clusters. Finally, we proceed recursively on each cluster until there is one cluster for each observation. There is evidence that divisive algorithms produce more accurate hierarchies than agglomerative algorithms in some circumstances, but is conceptually more complex. And in agglomerative method can be explained as follows. In agglomerative or bottom-up clustering method, we assign each observation to its own cluster, then compute the similarity, for example, distance, between each of the clusters and join the two most similar clusters. Finally, repeat steps 2 and 3 until there is one single cluster left. We have reached the end of this video. I hope you have clarity on model taxonomy in machine learning. Please share your comments as it inspires me to do further topics on machine learning and deep learning videos. Please share this video with your friends and colleagues, and I'll publish my next video very soon. Till then, have a nice time watching my videos. Bye.